So here's a great function to look at. The function is going to be defined by f of x equals sine x over x. My question is, what's the limit of this function as x approaches 0? Let's try to guess the limit by looking at a table of function values. So here's a bunch of input values that are getting closer and closer to 0. Right? 0.1, 0.01, 0.001. These are getting closer and closer to 0. And I'm looking at my output values for my function. Right? So f of 1 is sine of 1 over 1. This is sine of 1. F of 0.1, that's sine of 0.1 over 0.1. It's 0.99, a little bit more. F of 0.01 is 0.9999, a little bit more. And you keep looking down here, and these numbers seem to be getting close to something, right? 0.999999. This is really, really close to 1. So based on this table of values, you're tempted to guess that the limit of f of x as x approaches 0 is 1. Another way to gain some insight about this limit will be to look at a graph. Here's the graph. This is the graph of sine x over x. And you can see that when x equals 0, function's not defined there because I can't divide by 0. So I've got this little hole in the graph. Nevertheless, I'm claiming that the limit as x approaches 0 is equal to 1, which actually means that I can make the output as close to 1 as you like if you're willing to have the input be close enough to 0. Instead of talking about closeness, push this red button and turn on this red interval. So when I say close to 1, what I really mean is that the output is inside this red interval. And that red interval might be really big or it might be really small. But to be close to 1 is going to mean inside the red interval. The point is that you can turn on this blue interval, and as close as you want the output to be to 1, I can promise you that the output is within the red interval if the input is within this blue interval. When the red interval is really big, well, then that's not much of a challenge. I can have a really wide blue interval, and anything inside the blue interval has output landing inside the red interval. But even when the red interval is very, very small, there's still some tiny little blue interval so that whenever x is within the blue interval, the output is within the tiny red interval. In other words, even if you want the output to be really close to 1, I can promise you that the output is that close to 1 if you're willing to have the input be close enough to 0. So we've looked at the function values, we've looked at the graph, we've got this idea that the limit of sine x over x as x approaches 0 is equal to 1. But it's just that, it's just an idea. We don't yet have a rigorous argument that this limit is equal to 1. Here's a sketch of a more rigorous argument that the limit of sine x over x as x approaches 0 is equal to 1. It turns out that for values of x which are close to but not equal to 0, this is true. Cosine of x is less than sine x over x, and sine x over x is less than 1. Now, why would you care about this? Note, the limit of cosine x as x approaches 0 is 1. And the limit of 1 is 1, because the limit of a constant function is just that constant. So I know that the limit of this side is 1, and the limit of this side is 1. And what I'm trying to conclude is that the limit of the thing in between is also 1. And it turns out that there's a way to do this. Let's take a look. Here's what we're going to use, the squeeze theorem. Suppose you've got 3 functions. I'm calling them g, f, and h. G of x is less than or equal to f of x, and f of x is less than or equal to h of x for values of x that are near a. But maybe these inequalities don't hold at the point a. Also, suppose that the limit of g of x as x approaches a is equal to the limit of h of x as x approach a is equal to some L. So the limit of g of x and the limit of h of x are the same value L. Then you get to conclude that the limit of f of x as x approaches a exists and it equals L. Why is this thing called the squeeze theorem? Or some people call it the sandwich theorem or the pinching theorem. Let's take a look. Here's pictorially why this is called the squeeze theorem. I've got an example here. 3 functions, g, f, and h. And again, g of x is less than f of x less than h of x. Now note, the limit of g of x as x approaches a is L. And the limit of h of x as x approaches a is L. F is squeezed or sandwiched between h and g. And consequently, the limit of f as x approaches a is also equal to L. Now we're going to use the squeeze theorem to try to understand the limit of sine x over x. So we've got the squeeze theorem. And what do I know? I know that cosine x is less than sine x over x is less than 1 for values of x that are close to but not equal to 0. And the limit of cosine x as x approaches 0 is equal to 1. If you like, because cosine's continuous and cosine of 0 is 1. Also, the limit of 1 as x approaches 0 is equal to 1, because the limit of a constant function is that constant. So the limit of this function is 1, the limit of this function is 1 as x approaches 0, and that means, by the squeeze theorem, the limit of sine x over x is also equal to 1.